3, 2, 1.
Timed out. So a lot of our participants that responded to the survey had asked the question, um, what is fusion? How can you describe your fusion different than hot fusion? So what would you say to somebody in a way that we can share not our trade secrets, but definitely give some information that's useful for somebody that's listening?
Right. So safe nuclear fusion using the ARC reactor fusion on demand is 180 degrees different than what the hot fusion guys do right now. So hot fusion, they do this thing called bulk ion heating where they actually agitate the dielectric medium or the fuel source. And they basically get it up to 100 million degrees and they just thermally heat the stuff up. And then it ignites into a fusion event. And that takes place at about 100 million degrees Celsius or 10 keV X-rays. The difference that we do is that we use this thing called the ARC reactor fusion on demand, and we induce a instantaneous nuclear fusion. Instantaneous nuclear fusion can happen at room temperature, and it doesn't take bulk ion heating to induce the fusion that takes place inside the ARC reactor. And so that's our patented technology. It's trademarked, it's copyright protected, and also we just got the United States Patent Office to grant Quantum Kinetic Corporation the international class for the ARC reactor for 042 and also 037, which means that we can now officially disclose and talk about our technology openly to the public and have intellectual property ownership.
So tell us a little bit then about why others haven't figured it out. We hear and see that they're making big claims about the plants that they're building in the future they're setting out in 10 years from now. And they've been doing that for a while, as we know. It's always 10 or 5 years out. But why haven't they got the ability to translate this the way that we have? What are they missing? And what are their chances of ever landing on it?
Well, they have to figure out that there's a better way to do electrical circuits. I mean, like what they're using right now is they're using methods of colliding atoms together at high velocity, like smashing rocks together,
Mm-hmm.
and or using a hammer to smash rocks to make them try to fuse. That is a very prehistoric approach, not to be so mean.
No, it's not mean if it's accurate, right? This is still talking science,
Right.
correct?
And so we're trying to tell the world about a new type of electricity that induces a negative pressure. Basically, if you have like a Venturi, like in a carbureted engine where when the piston's pumping up and down, it's sucking air into
Mm-hmm.
it. Thus, you can actually have gasoline come in with it too.
Yeah.
So that's a negative pressure. It's a Venturi effect. We do that with the arc reactor. We create a negative differential pressure inside the reactor as the electrons are swirling down. And then that causes the nuclear fusion event at low power. Instead of taking particles and smashing them together and spooling them up, it just takes way too much energy. And it's like taking a big hammer. You got to bring the hammer over your head. That takes a certain amount of energy. And then you got to let the hammer drop
Yeah.
to cause it to occur. But we figure out a way just to like knock the golf ball into the hole with just tapping it, and it just falls in.
Okay, so we have heard, and the way that we have discussed it in the lab before, there's a cavitation process to this because there's a separation and a rejoining, and cavitation, that electro-physical transmutation, has taken place. Describe a little of that process, because I think people are going to be looking into this in classrooms and laboratories for years to come, because honestly, I'm not sure anybody can actually explain it today in a way that everybody would say, I can fully relate to that, because the science isn't as clear as it should be yet, right?
Yeah. So the easiest way to understand the negative differential pressure is essentially take a straw and get a cup and put some Coca-Cola in it and put the straw in the cup and suck on that straw. And what happens to the Coke? It goes into your mouth. That's all it's doing in a negative differential pressure. It's super simple, super easy. It's basic thermodynamics. There's no trickery. So if you're going to teach this in an elementary school, that would be the first experiment.
No, I think if you did it in elementary school, the first thing you'd learn is you get Coca-Cola nose burps and they kind of go, it's like.
Well, speaking of burps, actually, it's interesting because In the reactor, if you have it set at really low power, like I'm talking like half a watt of power and just leave it on for like a month, you will get little burps. And these burps actually create this really strange sedimentation. And the sedimentation is, it begins to burp itself. Like it actually starts, the sediment begins to burp hydrogen. It's almost like a synthetic coral is growing in the reactor.
Right. We discussed this between ourselves off camera, and what I found was we discussed the organic inorganic interface.
Yes.
And even without any sustained power to this, which would cause organic life and inorganic matter to produce bubbles and demonstrate this, without any power, it continues, which means what? There's life in there, is there
Yeah.
not?
So this is something that when I was in high school, when I was taking chemistry class, the thing that blew my mind or I didn't really understand was that there was a line between inorganic chemistry and organic chemistry. And when you ask your teacher, like, hey, what's the difference here? Like, they just say, well, organic chemistry is carbon, nitrogen, oxygen, that's it, more or less. I'm like, okay, fair enough. But if organic chemistry is just these basic carbon, nitrogen, oxygen, well, there's also inorganic carbon, nitrogen, oxygen too. So what's so different about those two elements or those atoms that make them alive or dead, right? And what we've discovered with safe nuclear fusion, aka arc reactor fusion on demand, is that when you do nuclear fusion with this negative differential pressure safely, there's a very small neutron flux, basically a cold neutron flux, a resonant neutron flux, which is the opposite of fast neutrons, which everyone else is doing. Instead of killing everything around you, you actually begin to create life itself from the reaction. It's just Mother Nature, like planets growing, asteroids growing. Matter of fact, asteroids have diatoms inside them, which diatoms are carbon, nitrogen, oxygen, iron oxide, alive matter. And so when you do nuclear fusion with the arc reactor, you begin to stimulate the organicness of matter itself into existence, which is always trying to do that. Like nebula are trying to form organic matter, planets, the whole thing, all of astronomy.
Right. And carbon is the basis of life, of course. And then we take nitrogen, oxygen, you have building blocks.
Mm-hmm.
Uh, would you describe the organic creation as, called it off camera, a genesis? It's kind of a beginning. Is this not natural, or is it something like the cavitation and then transmutation of elements when we do the application in our cyclotron?
Mm-hmm.
And as we saw from the results that we received from the lab on uranium 234, 5, and 8, when those were broken down and we had zero values throughout the rest of the periodic table, and then other elements started showing up. This was not magic, this was science. Yet here it was, and we can't explain that. This is that building block transformation. At what point do you think you might have a grasp of what's happening there in transmutation that could potentially be the beginnings of this organic from inorganic shift?
It's a good question. So the answer to that is essentially when you're doing a nuclear fusion event, there's a thing in science called proton to proton chain reactions. And so what that means essentially is that a proton and another proton, when they fall into each other, they make a heavier element. That's fusion. And that's proton to proton chain reaction. And when you do these hydrogen ions that start growing, they go from hydrogen to lithium to barium to, carbon, nitrogen, oxygen. It's just you're stair stepping up the periodic table.
Yeah.
And as you do that with this technology, you can turn the knob, the voltage up to, well, instead of doing just protons, and we're going to stop at carbon, we're going to go all the way to uranium. So go ahead and turn the voltage up all the way, and bam, we're going to start making uranium. Or you can keep the voltage way low and just work on that really soft neutron flux. And then you can actually you can go, okay, I'm going to stop at nitrogen. We're just going to make a lot of nitrogen. Maybe we're stopping to make a bunch of oxygen. Maybe we need oxygen in the atmosphere or want to colonize Mars. So you have now the ability to control on demand whatever elements you want to fabricate with this. And if there's other elements around the system, basically like if you have a a quantum kinetic well, which is a negative differential pressure sucking in, the heavier elements, as they get close, they actually spallate. What happens in spallation is like heavy elements basically break apart.
Mhm.
And because there's a pressure sucking them, it's like if you had a crack in a windshield and a bug hit right in the middle of your crack on your windshield, part of the guts will go through the crack and come inside, right? That's what happens. It's like it spallates the bug into the car because of the suction.
That's a great example, kind of.
It's probably really badly executed example, but you get
Well,
the idea. It's a
oh
visual.
yeah, and so, but this is when we were discussing this before, the Variac actually becomes kind of the easy bake oven of nature in a way, and the creativity that we can apply to this, because we can turn this into organic. We can also turn it into minerals. We can turn it into usages for cleanup of nuclear waste. We're seeing some things that are going to break some barriers in physics labs.
Oh yeah.
And I really know, and I firmly believe that once this gets out more broadly in the science community, there's going to be some doors that are going to be blown out because they just simply cannot grasp this fundamental of a change in something that's been so long standing, existing status quo, that something like this comes along and redefines an entire sector of physics. What would be the reaction in your Nobel Prize acceptance speech for,
It's kind of avant-garde, but okay. Yeah.
well, I mean, play this out. Let's say 2 years from now, and this is everywhere, and now people are talking about it. It's a bigger deal. Would we find that the uh, receptiveness of the community, because of traditional versus this modern, it's almost like a 21st century version of Madame Curie or something, where we're seeing some of the radical shift in something so basic that it's going to require kind of retooling in education systems and in science industry and so forth. How do you help propagate that in a manner that would be consistent with its application and reality? Because there's always the naysayers, even when they're looking at it. They'll hold fire and say that's not fire until it's burning through their skin.
So that's a multi-part question and answer. So we'll start with the beginning about the scientific community and the discovery and the Nobel Prize. So let's just go back to the arc reactor when it was first fabricated and designed by Russell Bobbitt, who was the guru designer at Marvel, prop master. So he was commissioned to make a movie and make a nuclear fusion reactor design
Mhm.
for Marvel for this 2008 movie called Iron Man. And so he called a bunch of different physicists and particle physicists and nuclear fusion experts and asked them, look, I got this movie I got to make, and I've got to get a particle accelerator in the size of my hand, and what would it look like, and what would be its design features?
Mhm.
And so they told him it would need to have magnets. It'd be a magnetic confinement. It would need to be a particle accelerator, like a stellarator. It would need to have high voltage, high amperage, and high plasma. And he says, okay, well, I'm going to do some research. Thank you for information. I'm going to go in the lab and I'm going to work on this design. And an artist made this, not a physicist, an
So
artist.
conceptualized as a for a toy or a prop,
Yeah,
correct?
for a movie.
Right.
So this, when Russell Bobbitt was finished with this and put it on the table, he saw it and was like, wait a minute, there's something very special about this. There was just some weird spirit feeling about how special this is. And so it made it into the movie, and it was a major success, and it was a great, Disney selling tool.
Sure. Yeah.
But the interesting thing about this is it's actually every single type of nuclear reactor design in one unit. It's got the stellarator, it's got the inertial confinement, it's got the inverse reverse field confinement, it's got the magnetic confinement, it's got everything that you could possibly imagine inside this design.
And that was the conceptualization for a movie
by an
Now
artist.
give us now the translation of science
So
using
yes.
taking a story and turning it into something that we're now looking at. We got here in the lab.
So what happened next was a scientist got in a really bad crash, and that was me. And I had these visions of like something, and I was like, "What is this vision? You better go do it." And this voice kept telling me to go do it. And eventually, I started working on electronics, and then we had the opportunity to wrap my coils around this device because I need to write a patent for it. And just looking at it, I was like, well, this looks just like what I need. It's a toroidal transformer wrapped around the electrodes, which is like, dude, that's perfect.
Mm-hmm.
So I bought the tiny little toy, wrapped it around, turned it on, and sure enough, it hit 100 million degrees within a couple volts. And I was like, well, there's nuclear fusion. Let's write the patent.
You
So,
kind of stand back for a minute and just kind of gawk at something that was presented as a toy or a prop and turned now into something that science can't help but marvel at when they see it.
well, and that's the funny thing is like we've been trying to talk to the academic community about this, and they just keep throwing it in our faces and saying, cold nuclear fusion is a dud. It's silly. It's dumb. No one does that anymore.
Yeah, so let's dig into
What?
that a little bit. Is that the stigmatism from a half dozen or dozen of others who have come forward claiming to have
Mhm.
cold fusion did not have it? There's a stigmatism because of the fraud effect. And what we're finding is those who have disbelief grounded it and heart clinging to it. So it makes it harder for the acceptance of a reality shift. You can't go and just say, I have it. Even when you're showing it on our videos, people are still saying, like, that's not true. You're not, that's made up. That could be created with AI or image generation. This is not what it is. Yet, how do we take and translate this for a potential investor, for example? And if they wanted to see this, what do you think the criteria is for them as someone who would be looking at this both as a critic, but yet a curious possible investor?
Yeah. So at the atomic level of the electron is where this operates for transmutation, electrophysical transmutation. You can't see that with your eyes because it's so small. I mean, we're talking like transmutation of elements that are occurring at the atomic level.
Mm-hmm.
So for someone to say, well, show me nuclear fusion. Okay, I'm seeing X-rays coming from a machine, but I'm not really seeing anything viable in terms of a commercial application. However, radioactive waste remediation, we have proven with our technology, can reduce uranium-234, 235, and 238 by 80% within 24 hours, which is those numbers are mind-blowing in themselves, but then someone can come along and say, well, you contaminated the data, or you didn't use the right detector, and so you can come up with a thousand different things to cut it down into little pieces.
Sure. Yeah.
But what people really actually want to know is how much energy, like how much electricity, how much power can you generate using Iron Man's repulsor technology,
Right.
which is what this is all about in the end. It's like, how are we going to generate electricity
Well, sure.
free?
There's a cost benefit analysis for development for an investor. They want to know, I give you $50 million. When am I going to see something that cranks out $1 billion worth of benefit to our company? But honestly, we're looking for the benefit of mankind, and we want to make sure that we're doing the right thing the right way. But that is a fair question to an investor. They would want to see this low wattage input produce this massive amount of energy, and we can demonstrate that. Will it, so our question and our quest is, will it be enough, and do we have enough time?
Well, historically speaking, when a new revolutionary technology is de- tested, not deployed, but tested, let's just go back to the telegraph in the 1900s, and then the radio. Well, there are two people that came up with the idea of radio. There was Nikola Tesla, who was living in America, and then there was Marconi, who was living in Europe. They both said that they could send a wireless transmission to a
Mm-hmm.
battleship out in the open. Everyone said, you're crazy. That's impossible. There's no way that can happen. Well, Nikola Tesla got his two patents in America. Marconi came over to America because there was a couple special interest groups that glommed onto him and bring him over to America. And they basically, it takes a certain amount of money, time, and dedication to get this technology, like the radio, into commercialization and be used in military, be used in defense or into home heating or whatever industry you want to use it for. But you can't just do it for free. It takes money to get over that hump. So the answer is we're basically in the infancy stages of nuclear, say, fusion, but this is like now.
Yeah.
But this is like taking us back to the 1900s. We need it. We need someone that's going to come in, help fund it, develop it to a point where we can actually deploy for Americans and all around the world. It's that simple.
Yeah. So what would be, to put a bow on this episode, tell me a little about the vision of the future, 5 years, 10 years from now, the deployment, the message of hope for the world. What we're trying to do here is we're trying to clean up our nuclear mess. We're trying to alter the usage of nuclear for benefit in the future, doing a proper technology that has the ability to heat, and as you mentioned, many other things. And oh, by the way, everybody wants a cleaner planet. There isn't a person alive that wouldn't say, gosh, we could get rid of carbon emissions and nuclear waste. I think that's not a great idea. Let's just stick with plan A right now. And it's like, let's make plan B plan A. I think that's a better way to go. But also we've discussed the future of where we go in exploration beyond here. And so put a bow on this and tell us the next 5 years, 10 years, whatever. What's your hope? What's your vision? How do you see this rolling out to everywhere?
When you have a new type of electricity that does the opposite of destruction, it does creation and it does healing and it does building and it has the ability to undo or basically time change. Like uranium falling apart, that's speeding up the time clock in a localized space.
Mm-hmm.
So we can now utilize this technology for healing, restoring, rejuvenating, undoing the past, and making a better future for not just ourselves now, but our children, our children's children, and the rest. And even potentially mastering the ability to colonize Mars and other planets and maybe either other solar systems. The technology here is only limited to the imagination. And if you coming at this from a place of like pure heart, like fusion is love and love is fusion. You don't have to force it. It just happens. And when you realize that Mother Nature wants to give you everything, you just have to know how to tickle the way that she wants you to tickle her so that she can give you mother's milk, because she wants to give it to you. And actually there's folklore about that. The Hindu have a story about basically Shiva giving her free milk all the time from the ocean. You just have to know how to move the snake coils in the right way, and she will give you everything.
Mm-hmm.
So,
all right. Well, this is a good start to the beginning of a journey of a few episodes that we're going to put together, and I look forward to where we're going with this. I know that we've gotten some input from viewers from the YouTube channel, and we're going to go through those. We're going to ask for more of these to continue to give us some guidance on what's the value for you and as our viewers. We're very interested in at least another, 5 or 6 episodes?
Yes. And if you have any specific things you want to talk about, like specifically, go ahead and mention them in the comments. Make sure you like, share, and subscribe, and share this with your friends, because like we have the ability now to change the world for the better. And if you want to save money on taxes, you don't want to have to like pay billions of dollars for radioactive waste, like this technology could save you tons of money. And that's what we're trying to do. We're trying to make a better world, not just for planet Earth, but like actually for your pocketbook. Okay?
Absolutely. Fixing the past and preparing for a future that does not dirty with carbon emissions and nuclear waste. So, is it okay if I just make this one last little comment? Towards the middle of summer or something, can we do a little build up to something that we know is special that's coming?
Yeah, I mean, let's just put it this way. Quantum Kinetics has officially put forward the trademark of the repulsor technology for Iron Man. So this technology of the energy coming out and energy coming out of the hand, we've already begun tickling that. So I am really excited. I know you're really excited because you want to bring it out of me, but So you guys should all stay tuned to
Oh
the
yeah.
upcoming episodes because there's going to be some amazing stuff.
Oh yeah. But wait, there's more.
So, all right. So thank you for tuning in. This has been really fun. My name is McKane Lee, and this is
Randal Bird, the Chief Operating Officer and President of Quantum Kinetics Corporation.
thanks for tuning in, and we'll see you guys next time.
All right.
Ciao.
Ciao.